All right, last problem here for section 15.6 is another nice application of flux integrals. This deals with heat flux. And so here the temperature T measured in degrees Celsius at the point XYZ of a solid ball of radius A centered at the origin is given by this function T of XYZ is equal to 100 times E to the minus x squared plus y squared plus z squared. The vector field F, which is given by minus k times the gradient of the temperature function, where k is some positive constant, describes heat flow throughout the ball. Our job is to compute the outward flux of this heat flow vector field F across the boundary of the ball. Okay, so I've gone ahead and computed the gradient of our temperature function here. It's a pretty straightforward calculation. And then when you notice here is that there's a common factor of minus 200 times this exponential term. And when you pull that out, you're left with just x, y, z there for the components of this vector. And that's just the position vector of the point x, y, z. So in other words, I can write the gradient of the temperature function as minus 200 times this exponential term times the position vector r. All right. Now, F then, this vector field that's measuring or describing heat flow throughout the ball. Okay, this is minus k times this gradient, so that's going to give us 200k times this exponential term times the position vector r. All right, so now note that if I look at this vector field along the sphere, okay, x squared plus y squared plus z squared is just a squared. So the exponential term becomes e to the minus a squared. So I have 200k times e to the minus a squared times this position vector. But now, right, I'm just restricting myself to points along the sphere. So this vector r is just given by the parameterization for the sphere. Okay, now the other big thing to notice, this is along the lines of what I had mentioned in the last video when we were looking at Gauss's law, is that now while I could go ahead from here and compute the flux integral using this parameterization, work perfectly fine, but it's just going to be a pretty long, messy calculation. The key insight here, again, just like we saw in part A of the last video, is that the vector field F is parallel to the outward pointing normal vector here, n. Okay, so n is this unit vector normal to the sphere. F is parallel to it. So if I take their dot product, notice, right, the magnitude of n is 1 and the cosine is also 1 because the angle formed by these two vectors is 0. And so this dot product is just the magnitude of our vector field F, and that's right up here, right? So that's going to be 200k times e to the minus a squared times the magnitude of our position vector on the sphere. But this thing just has magnitude A, right? Because it lives on the sphere of radius A. So I just pick up a factor of A. And the big takeaway here is that this dot product is constant on the sphere. So when I go to compute the flux integral, I'm really just integrating a constant. Okay, so this is, again, this is a common thing that you'd see in a physics course, okay, where this just happens to happen a lot. Okay, so you can totally just sidestep all the really messy calculations. Of course, this is not always possible, right? We're taking advantage of the fact that our particular vector field here is a radial field again, and we're integrating over a sphere. So there's tons of symmetry at play here. Okay, if I change, say, the surface to something other than the sphere, then I can't get away with this. But here I can, and so I definitely will get away with this while I can. So here, if I integrate this constant over the sphere, I'm just going to get this constant times the surface area of the sphere, which is 4 pi a squared. So we get a value there of 800 pi k a cubed e to the minus a squared. Pretty slick and cool, really. All right, that's going to do it. Thanks so much.